Before we go to the next and last kind of t-test, I want to tie one loose end. Before we leave lesson 24, look on page 177, and let's talk about something we introduced earlier, effect size. Remember effect size? There are two ways to calculate effect size, and the formulas are different for every kind of test, including every kind of t-test. We talked about effect size for a single sample t-test. We talked about that, but let's talk about effect size for an independent sample t-test. If you look on page 177, the two different kinds of effect size are D and eta squared. I think we talked about D last time. If you shave off all the messy algebraic stuff, you find out that D, and this is actually Cohen's D, C-O-E-N-S, Cohen's D is equal to the square root of the sum of the ends on top divided by the product of the ends on bottom. I'm sorry, that's multiplied by T. So let's calculate Cohen's D. Now, SPSS will not do this for you. N1 times N2 should be a 1. It's on page 177, about a fourth of the way down the page. Okay. So we know what our T value is. And again, we're just going to use the positive of that. So 1.778 times the square root of the sum of the ends, that's 15 plus 15, divided by the product of the ends, 15 times 15. So my slide rule tells me real quick that I can find my calculator. I get about 3.27. Anybody get that? Don't just believe me. I mean, I can be happy. What did you get? Well, okay. I sorry, yeah, 12 million. Okay. Were you lying, or did you really get that? Okay. For D, if you notice that right in the paragraph, we've got values of 0.2, 0.5, and 0.8. And that's the small, medium, and large. So since 3.27 is a good bit bigger than 0.8, we'd say this has a large effect size. That's one way of calculating effect size. The other way is eta squared. Now, some of our more advanced procedures will actually calculate eta squared for you, but again, it's a different formula for every procedure. This formula would not have worked for a single sample t-test because you don't have two ends. And that formula would not have worked for this one because we do have two ends. So the formula depends on what kind of test we've got. So, let's look at the other formula. And this is called ETA squared, or it looks like an elongated N. It's not an N. Don't call it N. Now, you can find this key on your Word program because, yeah, you have to go to symbols. Yes, it looks like an N, but it's not an N. So, ETA, that's the way you pronounce it, eta squared. Okay, so, this is equal to t squared for the numerator divided by t squared plus n1 plus n2 minus 2. Now, does that look familiar at all? Say yes. Humor me. Okay, what does it look like? You're hurting me. You're hurting me on the night. I feel bad. Well, what is n1 plus n2 minus 2? Yes, that's the degrees of freedom that we have. So this is t squared divided by t squared plus the degrees of freedom. So 1.778 squared divided by 1.778 squared plus 38. And again, jump on your slide rule and see what happens here. And I get a 0.77 about. If you look under the formula, you see the key number is 0.010614. That's my small, medium, and large. So, excuse me, it's still going to be a large effect size. I say this because the effect size is one of the things that you report in an APA write-up. You can use either one. Yeah, and again, remember the effect size is sort of like the words I use. How significant is the significance? Yeah, there's a significant difference, and hey, it is kind of a big deal. Well, there's a significant difference, but don't get too excited. Generally, when you have a significant difference, though, you'll have larger effect sizes. When you have a non-significant difference, you'll get smaller effect sizes. Okay, question was, why are the small, medium, large effect size different? Because it's a different formula. You get different numbers out of it. Look at this formula. You're dividing a number by a larger quantity. You're always going to get a number less than 1 on this scale. Where with the D, we got an example where we had a number larger than 1. So yeah, the scale's different. No, the question is why we use one over the other? I don't know. Just pick one, yeah. Pick the easy one. And there may be some mathematical reasons for picking one over the other. I'm not sure. Right. Now again, these formulas here that we just went over, they'll not be the same, but they're not the same as the single sample t-test. They're not the same as the paired sample t-test. Because we got different kinds of data. Just pick one. Use either one. Okay. Yeah, I noticed you weren't going to tell me what your calculator said on that one. All right. Okay, let's look a couple of places. First of all, where'd my whiteboard go? There it is. Okay. Excuse me. First of all, look on page 315 on the hardcover, Wit and Quit book. 315, chapter 15. Question was, where did I get those .01, .06? That was from Green and Salkin, right under that formula on page, whatever page I was on a minute ago. Page 177, Green and Salkin. And I think those numbers I think those are fairly consistent from one to the other, from one test to the other. All right. You see a bunch of words here. The chapter is titled T-test for two related samples. In parentheses, it uses the word repeated measures. Sometimes you see the word, Green and Salkin uses the phrase paired. I prefer the word paired instead of repeated, because a pair is not always one thing then the other. Paired. You might see the word, if it's not independent, it is, I bet you know this already, dependent. Or sometimes you might see the word matched. So we've got 1, 2, 3, 4, 5, 6, 5. I can't count. We've got 5 different terms for basically the same kind of test. Now, your example earlier of what if you measure your performance in a low stress condition and then you measure the same person's performance in a high, that's a perfect example of a paired t-test. Because the data you got 2 sets of data, but the 2 sets come from one place. In our example with the pre-test and post-test where we looked at gain scores, that's also a good example of paired data. Matter of fact, that would kind of work with repeated, because pre-test is, you take the pre-test, then you take the post-test, you repeat that. But it's still paired. I still like the word paired together. No, one set of students. It's one set. If we're talking about test scores, it's one set of students, but you got 2 different scores for them, for each student. Can be a pre-test, post-test, can be a math score and an English score. Just 2 different sets of numbers, but from the same people. You remember that EPO example we used a minute ago? Let's redesign the study just a little bit. If you look on page 317, actually, I don't like that. Let's set this up a little different. I don't like the way it says it there. Yeah, that's okay. Original 12, 14, 2, control. I don't like the order that it puts the data in, but I'll change that around for you. Instead of having 2 different groups, one group has the EPO and one group doesn't, let's measure people before they have the EPO and the same people after they have the EPO. That's kind of like a pre-test, post-test. Pre-test, post-test pretty much always a paired sample t-test. So, again, I don't like the way they order this data, so just humor me, and I'll just kind of give it a slightly different data. Not exactly, because those were independent groups. I'm going to have dependent groups. I'm going to say our first patient, well, I'm going to measure, first of all, non-EPO. That's like the pretest. They don't get it yet. And then I'm going to measure EPO. That's like the post-test. Person number 1 had an endurance score of 7 before he had the EPO. He had an endurance score of 12 after he had the EPO. That's the same person. Now, notice these in paired form, the pairs are side by side because there are 2 different measures. One's pro and one's pre and one's post. Person number 2 had an EPO of 3 before he had it, had 5 after he had it. Person 3 went from 4 to 11. Person 4 went from 6 to 11. Person 5 went from 3 to 9. And person 6 went from 13 to 18. Okay, these are two different variables. One is the pre-variable, one's the pre-values, one's the post-values. They're not measuring the same thing, so they're not in the same column. You do it when the data are paired together. By paired, I mean the 7 and the 12 are paired together. They come from the same person. That's a pair. A pair comes from the same source. The 3 and 5 are paired together because they both come from person number 2. Okay, one's pre and one's post. Sure, yeah. The question was, what if you have a pre and post that are the same test? Sure, that's fine. One's before you had the instruction, one's after you had the instruction. So the conditions are different. Now, I will say, this is a stronger test than an independent test. You're more likely to find significance if there is some. It's a little higher level test. By higher level, I mean there's less ambiguity here because you don't just have a bunch of pre's and posts. You do have a bunch of pre's and posts, but you know specifically how the pairs are. Well, look at a couple of the messy parts they look at. Notice T has a value of 7.35 in the turquoise box on page 322, right before the end of the box. So just remember that T is 7.35, and we're looking at the 0.05 level, so we're okay with that. So I'm going to go to Analyze. We're going to compare means, and now what do? I bet you know this one. This is a paired samples t-test. Now the box looks a little different. I have only 2 variables. They're paired together, so I'm just going to double click on one. I know it. Oops, reset it. It doesn't like you double clicking. So I'm selecting and moving the arrow, or clicking the arrow. I need them side by side because that's how they're paired together. Whoa. Yes, double click them both over, but they have to be on the same line. This is ready for a second pair, but I don't have a second pair. I need to make sure they're side by side. Let's reset it again. The easiest thing to do here is, well, I can't double click just one. I can double click both of them. Whoops, I can't either. Just select one, hit the arrow, select the other, hit the arrow. That's it. That'll always work. Sometimes you can take shortcuts on the others. The option, again, we like the 95% confidence interval. All I have to do is click OK and get an output. And I'm going to get an output that's very similar to what I was looking at before, with a little bit of extra information on it. I've still got my means and standard deviations. There's 6 in each one. I've got my move it over. Okay, try again. All right, I've got my means and standard deviations. The mean of the non-EPO was 6. The mean of the EPO, that's the post, is 11. Was there a significant gain? Well, if I look at my T and degrees of freedom and significance, what's the one thing I look at to tell? The significance is 0.001. That is a significant gain. So I'm going to write somewhere T for 5 degrees freedom. Where do you suppose they get 5 degrees of freedom? Harken back to the core. It's the same because it's the number of pairs minus 1, which is exactly the way we measured in terms of correlation. Matter of fact, it even gives us correlations in the output. My R is 0.919. That's a significant positive correlation. But I'm more concerned with the t-test. T for 5 degrees of freedom is equal to 7.319, and my p-value is 0.001. So yeah, there's a significant difference between the 6 and the 11. Again, the key thing is still this. The question is why do we have two significant? Because this is for the correlation. This is for the paired samples test. It also gives you at no extra charge a correlation. No, you don't really need the correlation unless you specifically want it. But if you do, I mean, pairs are easy to correlate because those are the kind of data that we did correlate. So it just kind of throws that in as a bonus. So you get a correlation. We're concerned with the paired samples t-test, the bottom part. The question is, will it always be two tails? Not necessarily. You might say, is there a significant gain, for example? Or is there a significant loss? I mean, for example, if you're going higher or lower, for example, I wonder about as cars get older, what's the age of a car and what's the gas mileage? Is it between 0 and 10 years old or 10 or more years old? That might be my group. And I compare the pre and the post, gas mileage when it was new and gas mileage when it was older. I would want to see if it goes down, for example, in that case. Or if it goes down significantly. Yeah, it can be directional to answer your question. More of an answer than you wanted. Okay, let's look at an example or two from Green and Salcott. Let's go to lesson 23. It would be under content, yes. 23 data file 1. Thought I pulled that up. There it is, yeah. Lesson 23, data file 1. The question is, I want to ask a bunch of employees two questions. How concerned are you with pay? Give me a number on a scale, Likert scale or whatever. The other question I want to ask is, how concerned are you with job security? Again, give me a number on the scale, same scale. Now, how concerned are you? Yeah. I'm really worried about my pay, or I'm really worried about my job security. That's the kind of question we want to ask. The scenario is set up on the bottom of page 169. Uh, 1 to 10 scale, here's how concerned I am for pay. 1 to 10 scale, here's how concerned I am for security. I wonder overall which is a bigger concern. Now, these are paired data. They're not independent because person number 1 is concerned about pay on the level of 4 and concerned about security on the level of 3. So the 4 and the 3 go together. That's paired. They're not just independent where you tell me how concerned are you guys about security, how concerned are you guys about the pay. I want to link those two variables together because the same person has concerns about both of them. So that's the way I want to measure it. So that's a good example of what I mean by a paired sample. And we'll look at some other ways that we might pair data together after we go through this example. So we're going to go to Analyze. We're comparing these. And I'm going a little faster. It's a paired samples t-test. And I get my box with 2 windows. And I want to move each variable over to the right on the same line. And I don't think we're told anything different about alpha levels or anything like that. So I'm ready to click OK and get an output window. And again, the only difference, or as my dad would say, the onlyest difference with this and an independent test is that just the data is paired together. You're still going to write the same kind of sentence in terms of, T in degrees of freedom and all that. It doesn't present it exactly the same way. They change the order a little bit, but okay, if I can move it over enough, we can, there we go. We've got it all in there now. So, here's my mean for pay and security. Pay is 5.67, security is 4.50. People tend to be at least a little more concerned about pay. I wonder if it's a big deal or if that's a big difference in the concern. Well, I'm going to write T for 29 degrees of freedom. Again, I've got 30 pairs. Number of pairs minus 1 is degrees of freedom. The T value is 2.827, and that gives a p-value of 0.008. That is less than 0.05, so there is a significant difference between the two means. Let me point out something else to you I've mentioned before. See, these are the part of the table that says paired differences. Where do you suppose that 1.167 comes from? That's the difference between my two means. So is that difference in mean of 1.167, is that a big difference or not? Yeah, it is. It is. And again, keep in mind, we've got a pretty good sample size here. We've got 30. I get nervous if you have less than 30. I get really nervous if you have less than 20 in a group. But after 30, if you look at those charts in the back of the WIT book, you'll see that what it takes to be significant kind of levels out and flattens after about 30. It doesn't change much. It's not twice as good to get 60 than 30, but it's a lot better to get 30 than 15. So once you get kind of past 30, that's sort of the minimum that you can actually do anything statistically with. Well, actually, I'll generalize that even more. For any group that you're comparing, the smallest group needs to be at least 30. I get nervous if it's not at least 30. I mean, I could be doing an independent t-test with two classes, and if one group is 30 and the other is 15, I get a little worried about that. If they're both 30, I'm fine. Go back to Whit and Whit. And let's look at some examples of some way we might pair groups together. If I can find the page I'm looking for. There it is. Okay, look on page 318, and let's look at progress check 15.1. Does this indicate a paired test would be in order or not? So we'll just look at A through D. We'll just go through these really, really quickly. Let me close this out so I can see if anybody's saying anything. Page 3, the bottom of page 318. Okay. All right. A says, I'm comparing the weekly TV habits of third grade boys and the third grade girls. Is that paired or not paired? That's not paired. They're independent because if you're one, you're not the other. Excuse me. Number B. Okay. And then we'll do 3 next. The number of cigarettes smoked by participants before and after an anti-smoking workshop. That's paired. I think that's like a pre-test, post-test. That's paired. So the same person smoking cigarettes before you're measuring and the same person smoking cigarettes afterward that you're measuring. Annual incomes of husbands compared with their wives. Well, you didn't say it with much confidence, so I'm going to give you a chance to reconsider. The comment was husbands and wives are two different things. That's true. However, they are paired together. That would be a paired t-test. That's exactly nor pre-test post-test the same either. If they're paired together, this is a tricky one. If they're paired together in any way, and you'll see a lot of things. D is a little more. D is another example like this too. If they're paired together in any way, it's a paired t-test. Because what that does, well, I'll tell you what it does with the next example. C is paired. Let me comment what I was going to say it with D. Problem-solving skills of recognized scientists compared with those of recognized artists, given that the scientists and artists have been matched for IQ. Here's what that means. I've got a bunch of scientists and a bunch of artists. I want to know who's got the highest IQ out of each group. I'm going to pair them together. I want to know who's got the next highest IQ from each group. I'm going to pair them together. Here's why you do that. If you do that, then you say, oh, well, you're controlling for the variable IQ. It's not just one group has a higher IQ than the other. It's not a function of IQ. You'll see a lot of research where they will compare students on GPA. If I've got two groups, who's the person over here with the highest GPA? Who's the person over here with the highest GPA? We're matching them. That's why I used the word match earlier. We're matching them on GPA. That way, my GPA is not the factor that's going to influence the results, likely. So if you pair them together in any way other than randomly, there's got to be some kind of reason to pair them together. If they're paired together on some reasonable basis, it's a paired t-test. Now, most of what we're going to see are fairly obvious in terms of just like pre-test, post-test. Everything's paired in this except for A. Now, if I took the boys and girls and compared them on grade average, or matched them on grade average, that would be paired. But it didn't tell me I'm doing that. Yes. Yeah, in that case, I like the word matched. Husbands and wives, they're matched together in a reasonable way. Because they're married. Well, duh. If you have a pair and a child, that would be paired, yes. Because that's going to control for the family unit. Maybe the family unit would influence the results. Well, if you match them together based on family unit, that kind of takes that out of the equation that could possibly skew the results. Yeah, but you'd have to have one of each. You couldn't do teachers and students. The question was, can you do teachers and students? Again, we're looking at paired individual scores. This is a paired t-test. Keep in mind, a t-test deals only with comparing two things. I can't match the teacher with everybody in her class. I can match the teacher with one person in her class because we're only looking at two things. If you match her with 30, you're looking at 30-some things. So a t-test compares two things. Now, you probably can't wait. So pretty soon when we talk about how you compare three things. I hope I'm feeling better another night, yes. I'm just going to talk through, I'll do at least one more example. I'm just going to talk through it, but look on page 171 and notice the formula for effect size. 171 of the Green Salkin book. Gail, I see your answer. I'm not sure which one you responded to. I didn't look at it at the right time. I hope that makes sense. 171, you've got the D and the eta squared again. Notice, again, they're slightly different formulas because you've got different information. Notice in D, it's simply the t value divided by square root of n. That's the number of pairs is n. For eta squared, you need the t value. It's the same thing. It's the t squared divided by the t squared, again, plus degrees of freedom. But degrees of freedom is here by n minus 1. So when you calculate effect size for a t-test, it depends. And what it depends on is which kind of t-test you're doing. Those are the formulas for effect size for paired t-tests. That's the chapter it's in. You can use either one. And 90-some% of the time, if you get small, medium, or large on one, you get the same small, medium, or large on the other. Only if it's really borderline on one might you have a little error to go the other way on the other one. Yes. Yeah, they have different scales. And again, I think those scales are the same for Cohen's-D that they used in the other tests. I think Cohen's-D always uses, I lost it. I think Cohen's-D always uses point 0.2, point 0.5, and point 0.8. And I think eta squared always uses, does it even say so here? Yeah. What was it? Point what? What point? Okay, point 1, point 6, and point 14. I think that's always true. Yeah. Okay. Okay. Two things I want to do before I close this session. I want to do one more example like this, then I want to talk about the t-test write-up, because that's one of the next things you have to do. Walk with me to page 174 and open up lesson 23, exercise 2. Lesson 23, exercise 2. There it is. I knew I had it open. And I'll do this because of a question about the husband and wives being paired together. Here's an example where the husbands and wives are paired together. I've got husband scores, I've got wife scores. So we're looking at the anxiety, and maybe this will help you make this a little more palatable too. I've got couples together, and they're infertile couples. I want to know about their anxiety levels. Who's more? It is important who you're matched up with or who you're married to in terms of what your anxiety level is. It's not just an independent kind of thing. It's a paired thing. It's related. So we've got, like for example, in the first pair, the husband's anxiety scale is 47, the wife's anxiety scale is 50. You have couples tend to act like each other. They're both high-strung or not high-strung or whatever. Well, it's just, they're paired. And look at couple number 2. Pretty high-level scores on both of them, but they're still different from each other. So let's run the numbers real quick. And so we're going to go to Analyze, Compare Means, Paired Samples t-test. I'm getting faster. Oops. Husbands, oops, I know. Already moved that over there. If you hit it twice, it doesn't like that. So I'm moving each person's, the husband's infertility level to variable 1, the wife's infertility level to variable 2, and they're side by side on the same line. I think we're okay with our default options. So I click OK. And, all right, here are our means. Average men's anxiety scale is 57. Average wife's anxiety scale is 62. Here's one where I think the correlation is interesting. Yeah, if one tends to be anxious, the other tends to be anxious. High, strong, positive correlation. But that's not what we're looking for. We're looking at the t-test, which involves these numbers. So T for 23 degrees of freedom, the number of pairs minus 1, is equal to 3.256. P is 0.003, which is less than 0.05. Therefore, there is a significant difference between the anxiety level of husbands and wives in infertile couples. The wives is significantly higher. So when you say in plain English, that's what you end up with after you get through all this number rigmarole. I will bet that you all, when you've read research papers or research or journal articles or whatever, you have seen this kind of thing in the middle of it, and you said, I don't know what that is. You just got to read on to the plain English sentence. Well, that's what it means. Now, I think it's important to notice because sometimes professional journal articles they're not always consistent with what they say with what the results are. You might see something like this that says there's no significant difference, and that's contradictory to what we just wrote out by hand. So you need to be able to look at things and see if they're consistent with what they're saying, because they're not always. Dr. Manfred and I had some really, a number of good examples to where, real articles where they just misinterpreted this, probably by mistake, but at least inconsistently. It's like I said at the beginning of class, there are always holes in any kind of research project you do, so we want to minimize the holes, and there's two kinds of research, bad research and worse research, and we're trying to do bad research. Okay. Well, R is equal to 0.822, and it's a real strong correlation because the p-value for the correlation is so small. The chance of that not being significant is about as small as we can measure with our 3 decimal places. Well, it does. The fact that the significance is very high is consistent with the other. Now, you might get a very strong negative correlation. That still would be consistent, because strength is just the opposite kind. So yeah, there's consistency between the two different, the correlation p-value and the sample t-test p-value. So you would normally, if you got something really different, I would question. I'm thinking, let's go back and look at the data again. One thing I see once in a while is I may see a p-value of 0.051 one place and 0.049 another place, where they're on opposite sides of that 0.05. That doesn't get me too bent out of shape because it's so borderline anyway. There may even be some round-off error in there somewhere. How are we at home? Okay, last thing I want to do is I want to talk about the write-up for a t-test. And I've got an example that I gave you under content. I'm just pulling that up right here. Again, there are 3 kinds of t-tests, but I'm just giving you an example of a write-up for an independent samples t-test. You'll see the same kind of information, whatever kind of t-test it is. You're still going to report the mean, the t-value, and the p-value, and all that sort of stuff. Notice I've got, how do I get rid of that? Okay. The research question is, and I've got 2 write-ups, one for when there's significance, one when there's not significance. Is there, and we're running close on time, but okay. Is there a significant difference between the amount of talking between people in high stress conditions and low stress conditions? This is similar to the example we ran from Green and Salkin on the first one from there. It's not the same. I think we changed a few numbers. We upped the n size and all that stuff. So is there a significant difference? The null hypothesis is that there's not a significant difference. Okay, so read through this with me. And again, you can use this same template. You can just change the numbers and change the description to what you're doing it with. An independent samples t-test, well, if it's independent, you might have a pair t-test, you might have a single sample t-test. So whatever kind of t-test you've got. Was conducted to evaluate whether the mean amount of talking under low stress conditions and high stress conditions. The amount of time spent talking was the test variable, and the grouping variable was the high stress or low stress. Or you could just say the grouping variable was the amount of stress. That's fine. The test was significant. Oh, there's that sentence. The t-value with degrees of freedom in parentheses and the p-value. The fact that it's significant is consistent with a p-value less than 0.05. Likewise, we're rejecting the null. Also, all 3 of those things say the same thing. And then I say, the students in the high stress condition, I give them means and standard deviations. Tended to talk less, because these are times, or percents, talk less than those in the low stress condition. Oh, I've got an extra parenthesis there. Take that out. And I report the confidence interval, the confidence interval for the difference of means. I report eta squared in this case. You can report Cohen's d. And in this case, it's a large effect size. So again, you report if it's small, medium, or large. And here's the plain English sentence. Students in the low stress group tend to talk more than students in the high stress group. And we show that with a box plot. Yes. I will again, yes. Okay. So I'll go back and do a box plot in a minute. Remember the legacy dialogues option and all that and all? Okay. It's been a while. What if it's not significant? Same research question, null hypothesis. Same description. But here I've got not significant. The p-value is larger than 0.05. We retain the null hypothesis. You can say either retain or not reject. I report eta squared, which is small. Again, if it's not significant, it's likely to be a smaller effect size. And then students in the high stress group, mean standard deviation, about the same, because it's not significantly different than the other one, mean standard deviation. Report the confidence interval, and notice in the box plot how close those things are together. That's because it's not a significant difference. Okay, real quick, how to do a box plot again? Please, okay. Questions about the wording of the write-up first. Maybe maybe it was a scatter plot I was thinking about. Okay. Okay, that's the one. Okay. Okay, we'll do a box plot real quick. Any questions about the wording of the t-test? You can use any t-test example you want other than the low stress, high stress that we've written up here. You can't do that one. You can do a homework question. You can do any of the examples we did today. You can do any of the 3 different kinds of t-tests. So you got a bunch of things to choose from. Okay, let me find a good example. I'll find lesson 24 here. I want to do a box plot of the game scores, but whether they're integrated or not. Remember that example? We go to graphs. We go to legacy dialogues. You can ask me why it's called legacy dialogues. I don't know. Still don't know. We're going down to box plot. You can use error bar. Those are very similar, but we're going to do box plot. And it's I can't remember if it's simple or close. I think it's simple. I think we leave it alone for the default. Right. In this case, we're measuring the gain for the 2 groups. Label cases by that's where our grouping variable goes. Okay. You were right. I know that throws you off when you're right. It throws me off too when I'm right. Doesn't happen that often. That's our grouping variable. I hope. We'll see if I've done this right in a second. Oh, no. I'm sorry. I think I want that to go in category axis. Something didn't sound right. Let's see if that gives us what I wanted to. Well, that didn't work. It should give me that box plot in and output window. Let's go to graphs, legacy dialogues, box plot. Maybe I clicked the right. Okay, maybe I clicked the wrong button. Category axis. I'm sorry. Yeah, category axis is the grouping variable. That's what I get when I don't practice these things. And you can copy and paste this from the output window. The grouping variable, integrated or not integrated. That's what goes in the grouping. That's what goes in the category axis. In the variable box is what you're measuring. Okay, let me say it this way. Yeah. The independent variable goes here in category axis. The dependent variable goes in variable. Because the independent variable is, well, are they integrated or not? That's what happens on the front end. The dependent variable is the results after that fact, what their gain scores were. So independent goes in category axis, dependent goes in variable. Okay, let me and then just click OK and you get your box plot. And when I get the box plot, I can select it, I can copy it, and I can paste it into a Word document. Yeah, that's your question. Yeah, well, you either right-click select, or you go with the edit stuff up here with cut, copy, and paste. However you cut, copy, or paste. Put that in your Word document. Yes. So that's part of your APA write-up. So for next week, you've got two things. You've got homework 7. No, let me see. Is it 7 and 8? You did 7 before, yeah. Okay, it's homework 8 and 9. Homework 8 and 9. Well, that's what I've got written down here. I didn't read it. Homework 8 and 9 plus the t-test write-up. Any t-test you want to write up other than the high-stress, low-stress thing. Any questions, comments at home? So assignment for next week, homework 8, homework 9, and you've got in your syllabus tells you what those exercises are. And then the t-test write-up. And again, submit that all to the drop boxes, the appropriate drop box. And put your name on every page, please. Other thoughts, questions, comments? Okay.